The reason that we're doing this and wanting to get more volunteers and to really take control or take ownership of our watershed is because of the massive government cutbacks that we've seen over the last few years. There just isn't the funding or the staff to do the kinds of things that government used to do in the watershed. We'll move on now with Dr. Gilles Wendling, who has been working with us for several years now on groundwater in the Englishman River and groundwater and surface water interaction. And excuse me, we're now working on mapping the bedrock aquifers, and it's I think we're ahead of the curve here as far as knowledge about groundwater in the Englishman River than anywhere else, maybe in BC. So I'd like to introduce Dr. Gilles Wendling, hydrogeologist.
Good evening. We need volunteers too, so people who don't want to count the fish, they can monitor the groundwater. A lot of the work that we have done was accomplished because of you and because of the people who provided their time and access to the wells, like this gentleman and his daughter. And a lot of information was collected on the river. Here we measured conductivity of the surface water to understand how it was connected to groundwater, key data, key information that it's one piece of information that allowed to build the puzzle. And this is how we move forward. What we have learned in the process in the last 2 or 3 years, so we have focused on mostly what's called the overburden aquifers, so the aquifers in the sand and in the gravel. And this is just an example of what we learned in the area of the regional park, where we were able, through our work, to measure the depth to the water table in order to build a map showing the isocontours indicating in which direction the groundwater flow. And that helped us in quantifying the participation of that aquifer to the flux of the river. A lot of the information was presented in the past and is available online on the MVI website. So I will just go quickly through the summary of what we have done. So we were able to delineate the footprint of aquifers. So we have identified almost like 12 aquifers, and they are indicated here, the footprints. Some are closer to surface, some are deeper. So you have aquifers at various depths. And we were able to identify in which direction the groundwater was moving in these aquifers and the slope of the water table, if it was steep or flat. So this is a big improvement to what was known, 3 years ago, 4 years ago. And we are still ahead of the province, because if you go online in the province, they are still limited to 3 or 4 aquifers in the area. We also created illustrations to show what happens along the river. So you are walking down the river in its first 5 kilometers. The estuary is at the end here. And so on the right bank, you can see aquifers daylighting along the banks, as indicated by my colored shaded area here. This is the elevation of the river, my blue line. And this is the depth in meters, 60, 40, 20. That's actually geodetic elevation. So we have aquifers that provide water to the river, groundwater to the river. And this is indicated by my arrows towards the river, and with the estimated flux of groundwater being provided by these aquifers to the river. And this flow is critical in the summer when the river is actually fed by groundwater, because it hasn't rained for a long time. We also, using this same format with the aquifers along the right bank and the left bank, be able to connect the aquifers to actually land surface. So these aquifers have recharge zones. So when you look on the right bank, For this aquifer delighting along the first 3 kilometers, this is the recharge zone of this aquifer. And on the left side of my dotted line here, this is the area which participate to the flux of groundwater to the river. So it was important to collect that information and visualize that information and to pass the message so people can understand. I mentioned that this information is available online, and I can follow who is looking at that information. And it's very interesting for me to see people in Kenya, in Pakistan, in the Philippines, everywhere in the world, looking at that information. Because surface water, groundwater interconnection is new. It's a new field, and people are very curious about how it can be done and how we should do it. So what we're doing here is not only benefiting us, it's also benefiting a lot of people around the world. And I'm proud of that. What's happening with the bedrock aquifers? So when we did the study of the overburden aquifers, we realized that there was still a big piece missing. There is a lot of groundwater moving into bedrock. And when you look at Mount Arrowsmith and the ridge, this is bedrock. And this is fractured bedrock. And it's a big surface. There is a lot of rain. The rain gets into the soil, but a big part of it gets infiltrating into the subsurface, and then it reaches the fractures and it moves into the bedrock. So we need to understand much better what's happening in the bedrock. And in the summer, when you walk down the river, you can see wet spots, and this is water moving in the bedrock and discharging into the river. When we did the detailed study of the first 16 kilometers, so the falls are right here, so we have the bend in the river right here. This in yellow is location where we could see bedrock on the riverbed, at the base of the river. You know that this is bedrock. This is bedrock by the bridge. This is Little Mountain. This is the big recharge zone. And we have information from wells which have been completed in bedrock. And we have observed and noticed that there is actually an upward gradient. So the pressure at depth is higher than the pressure at shallow depth. So there is a movement upward of the groundwater from the bedrock upward. So it's very important, and the role played by bedrock aquifers is very important in this watershed. This is a map which shows the type of bedrock. This is a bedrock map. So we have the main stem here, and we have many tributaries. So you can see that we are dealing with different type of bedrocks. It's not just one type. And not only there is different type of bedrock, but there are many faults and fractures. There is a key fault right here. So you can see the Englishman River didn't end up there just by luck or by chance. It actually followed a weakness in the bedrock structure. It's why the river is flowing there. We have also in some tributaries, we have a fault right here, and we can see the tributary is following exactly the fault. So same thing, the weakness in the bedrock is driving how water flows at surface. We have many dots on that image, and all the red dots indicate wells which are completed in bedrock. The next slide. These are some of the wells that we have identified, and we have already equipped some of these wells with data loggers, and we are looking for more. So if you have a well completed in bedrock, raise your hands. Or if you know people or neighbors who have bedrock wells, let us know. We are very interested, because this is what we will install in the wells, just a little piece of equipment like my pen, and it will monitor the water column in the well and the fluctuation of the water column. So we'll be able to see how high the water gets into the bedrock wells and how low it gets. So with that, similar to this map that were produced showing the high water level and the low water table in the shallow overburden aquifers, we want to repeat the same exercise with all the wells completed in bedrock in order to see which areas are more fractures, lead fractures. Is the pressure high? Is the pressure low? And this is what will help us in generating maps showing the groundwater regime in the bedrock aquifers. Changing subjects, I wanted to tell you about the results of a study that was done by NRCan, Sharon Provencher and Steve Grasby. They did a study where they collected surface water samples and groundwater samples, and they wanted to see if they were connected using geochemistry, using parameters intersect to the water. I'll go very briefly through that. So this slide indicates the concentrations in certain ions: calcium, magnesium, sodium, potassium, chloride, carbonate, sulfate, and nitrate. So these are some of the key molecules in the water that help us to fingerprint water. And they sampled at different times. In the summer, 210, fall 210, winter 11, spring 11, summer 11. And they have also a set of samples for groundwater. They sampled surface water at up to 16 locations along the river, and they collected groundwater from 50 wells. So this graph shows the concentration on the left here on the log scale, 110, 1.1. And so for the various events. Let's start with groundwater. So groundwater, you clearly see that this is all the samples of groundwater are the ones indicating the highest concentrations of these ions. So groundwater is more loaded with all these molecules because there has been more time for the bedrock and for the sand and the gravel to provide all those molecules to the water. And groundwater moves much more slowly than surface water, so there is more time for exchange. What we see too is that the lower curves here is for the summer 2011 and the spring 2011. And so that will be the curves indicating a lower loading in this molecule. So this is water which is closer to rainwater. And for the samples collected in the fall, we have a fingerprint which is very close to groundwater, indicating that in the fall we have more groundwater getting into the river. This is a similar type of results, and they use what's called a Piper plot. The Piper plot is a very convenient tool and tools commonly used when we want to compare surface water to groundwater and look at the origin of water. So here the upper diamond is a summary of the results, and then you look at the various types of molecules. This is sulfite and chloride with an increasing concentration, 20%, 40%, 60%, 80%. And if the sulfite and the chloride increases, then you have a reduction in carbonate. Same thing if you have an increase in calcium and magnesium, then you have a decrease in sodium and potassium because they are opposite types of ions. And you can take this information and break it and detail it with the presence of sulfate or chloride. So we'll just zoom a little bit on this corner of the graph. So we see that first we have a very low percentage of, this is sulfate. So all our points are in the zone of less than 20% sulfate. So we have very little sulfate in the water, both the surface water and the groundwater. The colored points are for surface water, and the gray points are for groundwater. So we see that the groundwater is focused in a cloud, which is very clear on this, in this triangle, where most of the groundwater is in this corner here. So we are dealing with a high carbonate and low chloride water. We have 2 points here of surface water from the Englishman River. And here you can see that it's a high concentration of chloride. So these samples were taken close to the estuary, and you can see the presence of seawater and the mixing with seawater, which explain this high chloride and low carbonate. We have also an interesting lump of dots right here, and this is for summer 2011, and you can see it's not really connected to our groundwater. So we are, even if it was summer, they probably collected most of the samples following a big rain. So they mostly collected rainwater and very little groundwater. So it's a little complex, but I just wanted to let you know that this work has been done and it's available, and this is how they presented the information. There is one piece missing that I would like to get, and that they didn't give the key about the location of each dot. I would like to know, we know that it's close to the estuary, but I would like to know all the other dots on my graph. Are they at 3 kilometers, 5 kilometers, 8 kilometers, so that we can even detail the level of understanding of this geochemistry. We need people. Why? Because we want to understand better the connection between surface water and groundwater. This is a slope with gravel on top. I have like a seal cover, and this is my aquifer. Groundwater is moving in my aquifer and feeding a ditch, a stream, a lake. This can be 50 centimeters wide, or it can be 2 kilometers wide. It's the same principle. Groundwater will provide water to surface bodies. This is the elevation of my water table here. And so the flux moving through my aquifer will be a function of how high my water table is and the slope of the water table. So we need to understand better and to monitor better the location of the water tables near streams. And we can at the same time measure the temperature, the conductivity, and many parameters from that stream to better understand how much it is getting from the aquifer and its overall fluctuation of the quality over time. Because fish will need cold water and they will need clean water. So this is where the understanding of aquifers, surface water, and fish go together. We try to characterize the presence of the aquifers in the region. This graph shows the bedrock at depth. The light blue indicates aquifers, conductive sand and gravel material, and the gray indicates till low conductivity material. This cross section is located here. So we have the coast. This is the old highway here with the orange bridge. And we have the Parksville well field here. Little Mountain would be right around the corner, just to give you an idea. This is the elevation due to the fact we're getting too close to Little Mountain. What I wanted to show in that slide is that there is an area, this is the elevation of my water table in various aquifers, but you can see in this zone corresponds to this zone here. We have water table at relatively shallow depths. In this area, the water table is extremely poorly defined because there are very few wells and it got paved quite a few years back. So we know very little about the condition of the groundwater in this area. There are some very good chance that the groundwater is very shallow, 1 meter, 2 meters, 3 meters. You don't have to dig 20 meters to get to the water table. And so it's an area that we would need to understand better. So I have highlighted with my purple rectangles zones where I'm curious to know more about groundwater and surface water. For example, here we know that we have ditches that we would like to rehabilitate. We would like to recreate good habitats. As I mentioned, the water table is very shallow and groundwater is key to the flow present in that stream. So we don't have to dig 20 meters or drill 50 meters to put a well in. We just need to go 1 meter, 2 meters, 3 meters, and we'll be able to bring more pieces to the puzzle. We mentioned our Shelley Creek was a great tributary. Lots of fish found in this section. Same thing, I want to know more about what's happening with groundwater and surface water interaction. And as a zone of interest is this zone here. We have wetlands, we have the birth of a stream right here. Why is the stream starting right here? Probably it's fed by groundwater. We want to know more. And we want to protect the land around it. Wetlands are extremely valuable land. So what can we do? Back to my illustrations here. We can dig or actually drive what's called drive points, which end up like that. You can see this is a foot, so you can see the scale of the thing. And we can drive it down to 2-3 meters, and we'll create little wells like that. And then every second week, every month, we can go there and monitor the depth to water. We'll be able to define our water table. And at the same time, we'll collect information on water quality here. We'll know the water table more, we'll know the aquifer better, and we'll know the quality of our stream better. Simple, very important. Thank you. That was my talk.